Really 4 kinematics equations, but one of them is so rarely used that I really don't bother giving it to you. Okay, we never use it, and it's just an average, so we know how to calculate an average anyway. So the way that these kinematics equation works is that the only time we can use them is when we have what we consider constant acceleration. Okay, so constant acceleration, that seems kind of counterintuitive, right? What does acceleration mean?
Increasing.
Yeah, and not necessarily just increasing speed, but a change in speed. Any sort of change in speed is considered acceleration, right? It can be speeding up or slowing down. Both types of acceleration. So we have to have constant acceleration, which seems strange because it's a change, right? But what that means is that in this set of equation, when we're going to use this equation, we have to have a constant acceleration. We can't be speeding up and then slowing down and then speeding up some more and use it in the same equation, right? We'd have to break it down into 3 sections if we were going to solve that problem. Okay, so during a problem, you have to make sure that you have constant acceleration or uniform acceleration. Okay, so these are called the kinematics equations for constant acceleration, otherwise just known as your kinematics equations. Okay, and I'm going to give you 3 big ones that should go on your equation sheet. Okay, none of these equations are valid unless we know that acceleration is constant. Okay, which in all of our problems, right, it's going to be. There'll be a few problems we got to break into pieces, but for the most part, it's going to tell you, right, if acceleration is this, solve blah, blah, blah. Okay, so it's going to be pretty straightforward. That's not something that's in there to try to trick you. Most of our problems will have constant acceleration. So here's our first kinematics equation. V equals V sub O plus AT. We'll go over what these variables mean here in a second. Okay, so your book gives the equations in this format, using V sub 0. Okay, and what that means is that it's our initial. The reason it gives it in that format, sub 0, is because this is essentially telling us that when time is 0, right, at the beginning of our motion, this is the velocity. Some books, like the other physics textbook we use, just have V sub F and V sub I for final and initial. For some reason, your book chooses not to do that, so I go with what your book says. So this is our initial velocity, making this our final velocity. Okay, final velocity. So without a subscript, 0 is always going to be our final. Okay, and you'll see that 0 subscript in a lot of other things. But anything without that 0 subscript would be our final. Okay. A then should stand for what?
Acceleration.
Acceleration. And T is standing for time. Okay, so let's talk about these equations and their units. Okay, velocity needs to be meters per second. Both velocities need to be meters per second. If that's the case, what does acceleration have to be in?
Meters per second.
Good, meters per second squared, which means time has to be in seconds. Okay, so in order for these equations to work, you have to have consistent units running throughout the whole problem. So you can't have velocity in kilometers per hour and time in seconds. It's not going to work. Okay? I'll show you where this equation comes from. Okay, this is just a rearranged version of another equation that we learned. Last time we learned acceleration is equal to change in velocity over time, right? Which is essentially acceleration equals V minus V sub O over T. If I rearrange that equation, times T, right? And I add over V sub O plus V sub O, right? That's equal to final velocity. That's what we just got, right? So that's where that equation comes from. It's just rearranging that acceleration equation. Okay? Questions here? This works if we have constant acceleration. I'm going to give you all the equations first, and then we'll go back and solve some problems with each. Okay? Yeah?
So if you had a problem where you needed to use that, and say you just used the one that we did last time, it's not
No, perfectly fine.
Where we're going to have to use this one.
Mm-mm. We're going to use these 3 so often that these will be the 3 you'll feel most comfortable with, but it's just the same version of that other one. Yeah?
So do you not use this one ever with like kilometers per hour? Do you always want to change it
You always change it to meters per second. Yep. Yep, so that we always are going to be changing meters per second. The equation that you could use kilometers per hour with is when we have constant velocity is equal to distance over time. So this equation is only used when we have constant velocity. Anytime we have change in velocity, we've got to use acceleration. But anytime we have constant velocity, we can go back to that very first equation that we used. Okay? So our second kinematics equation gets a little more intense, a little more complex. X equals x sub o plus VOT plus 1/2 AT squared. A little more intense. Again, you'll get these equations on every quiz and test, so it's not a huge deal. But we need to remember what these variables are standing for. Okay, what did we decide that X stood for? Displacement, good. How far we ended up from where we started. So if those are both displacement, this is our initial and this is our final, right? Sub-zero is initial. And something I'll kind of point out about this problem is that most of the time, x sub o is going to be 0. Because wherever we start our motion at, that's our initial position. That's where we put the origin. So we're calling that 0 anyway, right? We don't say we traveled from a 10-meter mark to an 80-meter mark. That's not how we word questions, right? We say we traveled 70 meters. So 70 meters would be our final displacement. 0 is our initial displacement. Does that kind of make sense?
Yeah.
Okay, so if I am starting a motion here and I'm going right here, this would be my origin, right? So my initial displacement would be 0. My final displacement would be whatever that distance would be. Does that make sense? So more often than not, this x sub o would be 0. Okay. Everything else here we've talked about. So only using initial velocity here, this whole equation we can solve without knowing the final velocity, which is a plus. Okay, because sometimes we don't know the final velocity. So this equation is without final velocity. Still have time, still have acceleration. So something I want to point out about this equation is that only the time unit is squared here. Okay, so out of this term, right, it's not like the whole term is squared. Just the t is squared. And like you might want to circle that square because a lot of people solve problems, and if it's wrong, the first question I ask is, did you square time? And most of the time we say, no, we didn't. Okay, so just make sure you keep that in mind. Okay, t squared. The last of the big three here, v squared equals v sub o squared plus 2a delta x. Do we notice a variable missing here? Yeah, we don't have time. So this equation is helpful because sometimes we're not given time in our problem. So this equation we can use to solve without time. Okay, so there can be parts missing, and we can still be able to solve for it. What's one variable, actually two variables that run through every equation?
Velocity and acceleration.
What type of velocity? Initial velocity and acceleration. So those are two things we have to have in every problem. Okay, it could be that we have to solve for one first and then plug it in, but for the most part, we should have those two things in every problem. Okay. And I'm going to give you the last equation. It's not really it's one of the kinematics, but it's used very, very little. This is not one that we probably need to put much focus on, but it's just a true average of our velocity. Okay, it's literally an average. So final velocity plus initial velocity over 2. There's rarely instances that we need to use this equation. Okay, but still put it in your notes. I don't know that I would necessarily bother putting it on your equation sheet, but have it in your notes just in case there's a homework problem about it or something crazy. The line just means average. Yeah. Problems. It's really important that you read the entire problem. Don't read halfway through and assume you know what it's going to ask. because you could be wrong, right? And then you're wasting time. Or it could ask for something really simple and you did 3 equations when you didn't need to do any, right? So just make sure you read the whole problem. We need to get used to drawing diagrams, and they can be very, very simplistic diagrams, right? So I'm talking like if I'm standing on a cliff or a hill, right, and I throw something off the hill, right, that's as intense as my diagram needs to get, okay? Very, very simplistic. This is where I would draw my origin, right, because it's where my motion is starting, and my object's going to go up and then land below where it started, okay? So just think about these little diagrams. They can be very simplistic. Write what you know and determine what it is you need to be solving for. Okay, so if your problem is worded in a way that says, how long does it take? What does that mean we're solving for? Time. If it asks you, how far did they travel? We're solving for displacement. What speed did they finish at? Velocity, right? So things like that you need to be looking for. And again, I'll make my list in the margins of our variables, and I'll question mark the one that I think we're solving for. Last thing, we check to make sure our answer is reasonable and if it has the correct unit. So I will warn you, in high school physics, sometimes we get unreasonable answers because sometimes I make up problems and sometimes they don't make no sense. But for the most part, we should be looking for reasonable answers, right? And then make sure you include your units. Let's try one here. All right, we're designing an airport for a small plane that must reach a speed of 27.8 meters per second before takeoff. This plane accelerates at 2 meters per second squared if the runway is 150 meters long. Can this plane reach the proper speed to take off? So this is a little bit tricky, right? We've got a couple different things that may work together or they may not. So let's write down what variables we have so far. Oops. Okay, when we're talking about takeoff, right? 27.8, is that our initial velocity or our final velocity?
Final.
Our final, good. So that means our initial velocity is probably what? 0, good. Our initial velocity is 0. Our acceleration is 2 meters per second squared. And we know the runway itself is 150 meters long. But we're asked the question, or we're posed the question, is the plane going to make it? Okay, so we can solve this a couple different ways. We can solve for the final velocity of the plane after 150 meters and see, does that velocity match? Is it high enough? Or we can solve for the displacement it's going to take to reach that 27.8 meters per second. There's 2 ways you can go about solving this problem. Which makes more sense to you, or which would you prefer to do? The displacement one. Okay, so that means we're throwing out the 150 for right now. We're not using that in our equation. We're going to see how many meters does it take to get up to the speed of 27.8 meters per second, and then we're going to see, is it long enough or is it not? Does that make sense?
Yeah.
Okay, so that means we're solving for our final displacement. That's right, that's right. X of O would just be 0, right? Because the beginning of the runway is where our motion is starting. So what kinematics equation can we use here? Or which one should we use? The third one, right? Do we have time? No, we're not given time, so that's our only option, right? We can only go that way. If we want to just do one equation, right? We can go backwards and use all 3 equations if we want, but there's really no reason to do that, right? You can use the first one to solve for time and then plug it in somewhere else, but there's no reason. So v squared equals v sub o squared plus 2a delta x. sure we're using that square here. Yeah, Colin. Oh, okay, sorry. So squaring this gives me 772.84 equals 0 squared plus 4 times x. Right, so I'm dividing that 4 over, and that's telling me that in order to reach a speed of 27.8 meters per second, we have to travel how many meters? 193.21. Okay, so is it gonna reach that in 150 meters? No, so that means our runway is not long enough. So can it reach the proper speed? No. Right, we're answering the question as no. So see here, it would have been very easy to plug in 27.8 and 150, and then you would have been like, well, what are we solving for, right? Just because a number is given to you, you really have to evaluate what's the question asking and what numbers should I be using. Does that make sense? Okay. Very good. What length does the runway need to be? Okay, good. We already solved for that. Perfect. 193. Any questions on that first problem? Okay, good. Car starts from rest and accelerates uniformly for a time of 8.41 seconds for a distance of 230 meters. Determine the acceleration. So we're taking a step back here, a little bit simpler.
For time we have 8.41.
Good. Madison, can you give me another variable? Good. Is what? Good. 0, because it says it starts from rest. Jake, what's another variable we have? Displacement. Initial or final? Final is what? 30. What's our initial displacement? 0. So what are we solving for? Acceleration. So what kinematics equation could we use?
The first one,
Why the first one?
because you can solve for acceleration using multiple.
Do we know our final velocity?
Oh,
No. Got to be the second one, right? We don't know how fast it's going at that 230 meter mark, so we've got to use the second one. We don't know our final velocity. We know our initial, we know time, we know our displacements.
Gotcha.
When our initial displacement is 0, or sorry, when our initial velocity is 0, it makes these questions really easy, right? It makes this equation really easy. Yeah, agreed here? Okay, do we see the math that's going into that? We did 8.41 squared times 0.5. Then we're dividing that over to the other side. So 230 divided by about 35.4.
Does the not multiply into the A?
Yeah, it does. So I took 8.41 squared, and then I took that times 0.5. Because this is all one term. Right? 1/2 times A times t squared. So that would leave me with 35.36A in that term.
Oh, yeah.
Does that make sense? And then I divided it out to get over.
Okay, everything just
Okay. Notice how one of your kinematics equation is time 1/2, and one of your equation is times 2. You have to be careful with that because I'll see people just do the wrong one. They'll multiply by 2 instead of multiplying by a half or whatever. So just make sure that you're being careful and consistent when you use your kinematics. Okay, try this one on your own. It's 2 parts. Determine the acceleration, then find the total distance we traveled from start to finish. Okay, so it will take you 2 equations to do this. So did we agree on the acceleration part, 7.56?
Yep.
The first kinematics equation to solve for acceleration. Second part, how many of you used the third equation to solve for displacement? Did you get the same answer?
Yes.
Good. Okay, so it doesn't matter which one you use. Once you have every variable available to you, it doesn't matter which one you use, which equation you use. They're going to work the same. Okay, any questions here? Okay, very good.